Okay, in the last video, we covered and introduced Newton's law of gravitation. In this video, we're going to be continuing with the topic, but now introducing the concept of circular motion. Now, it's very important because we are asked that we should know how to analyze circular orbits in gravitational fields and relate the gravitational force to the centripetal acceleration that it causes. So it's important for you to understand how circular motion relates to gravitational fields. Now, most planets and satellites have a near circular orbit. In reality, this is not true, but for physics' sake, let's assume it is. The gravitational force that is between the two planets can provide the centripetal force. So let's assume you take the Earth. So this is the Earth over here, and this is the Sun. As the Earth orbits around the Sun, the Earth will be doing that because of the force of gravity. So the force of gravity is essentially a force that acts between the Earth and the Sun. Now, the Earth is now going to experience circular motion. It's moving in a circle around the Sun with a force perpendicular to its motion. So its motion is going to be in this direction with a speed v. So now we can assume that the force of gravity is providing centripetal force. Isn't that interesting? So now we have that fact established, we can derive an equation that can be used to calculate the centripetal force, which is so exciting, right? So first off, we start by understanding what is the centripetal force. So the centripetal force is essentially mv squared over r, the product of the mass, velocity squared, divided by the radius. So after we have that fact established, we cement that. Now, we want to equate the gravitational force to the centripetal force. This is very important because we've said if you're in a circular motion, the Earth is going to experience a gravitational pull. So those two forces have to be the same. Okay, so the force of gravity will be equal to the centripetal force, right? So if we have gmm over r squared, which is equals to mv squared over r, we can therefore be able to have that fact established, right? We've already talked about what the gravitational force is by looking at Newton's third law. Now we can cancel out the masses, so this m and that m, and we'll be left out with gmm over r squared, which is over here, and v squared over r, which is over here. Then we can multiply both sides by r, right? So you can multiply this side by r, multiply that side by r. So the r's will cancel out, so that will happen. And essentially you'll be left out with gm over r is equivalent to v squared. Okay, so now you can either solve for orbital speed. So you can be asked, what is the v, the speed that the Earth is moving with? So v will be equal to the square root of gm over r. So it means that no matter how big the satellite is, it's going to travel at the same speed in a particular orbit that has a radius r. It doesn't matter how big that satellite actually is. What I mean by this is, for example, if you have the Earth at the center like that, then you have an orbit which is like that, right? So if you take a satellite which is yay big, right, and say satellite S1, and then take another satellite which is yay big, and then say satellite S2, both S1 and S2, despite having varying masses, will actually have the same speed, right? Because it's independent of the mass of the object, right? You need to consider the mass of the thing at the center, which was the Sun, and the radius itself, which is the radius of that specific orbit, which will be r. So that's something that you need to be considering. Okay, so we also have another equation that we need to talk about, right? So in some questions, you'll be asked to derive this equation, questions that we're going to explore together. You also have questions where you have binary star systems. We're also going to explore those questions together. But for now, we're going to derive what is known as Kepler's third law for planetary motion. So Johannes Kepler, a very smart guy, came up with a law that we're going to derive together. His point was, for planets traveling in a circular orbit about the same central systems, the square of their time period, so if you take their time period, you square that, is going to be proportional to the cube of the radius. So in other words, what I'm saying is, if you take the time period, the time taken to rotate around that object is going to be proportional to the cube of the radius of that orbit, right? So it's a relationship between the period, the time taken to complete one oscillation about a planet, and the radius of that orbit. Okay, so first of all, we need to derive this because questions will ask you that. So the orbital speed definition for one orbit, The speed is the distance traveled in a given time period. So since it's a circle, the distance traveled is 2 pi r, which is the circumference, divided by the period, which is t. So v will be equal to 2 pi r over t. Now, whenever you're asked to derive this equation or some variation of this law, you need to state this following statement. It's a given mark every single time. You have to state that the gravitational force provides the centripetal force. Okay? Then now you're going to equate these two things. So GMM, like what we said, should be equal to mv squared over r. Okay? So you're going to cancel m throughout all of this. So this m and that m cancel out. We've done this before, right? So left gm over r is equals to v squared. But now there's an interesting thing here. We know v is equals to 2 pi r over t. So now I can replace v and put 2 pi r over t. So square that, and we're going to end up with 2 squared, that's 4. Pi squared r squared over t squared is equal to gm over r. Okay? So now we can make t squared the Sabito formula. We multiply by t squared over there, 2 squared over there, and then we divide. So essentially what I'm doing here is multiplying by r. So I have 4 pi squared r cubed being equal to gm t squared. Okay, and my goal is to rearrange for t squared. So you can now see that okay, t squared will essentially be equal to 4 pi squared divided by gm r cubed. And you can see that all of this is a constant, right? All of this is a constant, which therefore implies that t squared over here will be directly proportional to r cubed over there, right? Which is Kepler's third law. So this is essentially what Kepler's third law is all about. Kepler's third law is about you understanding the relationship between the period, the time taken to complete one oscillation, and the radius of the orbit that you're in. And you need to understand that the gravitational force can provide the centripetal force, which is an important realization that we first started with, and derive this equation for orbital speed. You should also be able to derive the equation for the time period, the time taken for a satellite to orbit around the Mars. But that will essentially be it. I'll catch you in the next video where we talk about geostationary satellites. And again, if you're interested in this document that I'm using throughout this video series, you can easily purchase it on my Patreon. It's an entire book that covers all the different topics in A2 physics. You can purchase it on my Patreon. I've put the link in the description below. But until then, I'll catch you in the next one.